All right. So something that we are going to study today is basic concepts of thread. We'll look very briefly about it because whole idea was to create a top level view and then go on explaining that in subsequent lectures, right? So today we'll try to cover these two concepts. That's a dual mode of operation and thread. Okay. All right, and we will briefly look at the concept of multi-programming, multi-processing, context switching, etc. Okay, so this is what we have learned so far. Fine. So this is what we discussed yesterday, and all right. Okay, this is how. Okay, these concepts we have covered. Okay, this diagram we studied last year, if you remember. Okay, and what does it say? The processor operates in virtual address space. Okay, so basically each process thinks that it has all address space, and then only at the runtime the translation happens. Okay, you would have, if you recall, there was a diagram where for there is a continuous translations keep happening. Okay, so this is a translation happening here by memory manager. Yes, yeah, sorry. Okay, and there I'm sure there should be something like this here too. Okay. All right, so each process uses its own address space that we have discussed several times, and we're just repeating so that it goes to your mind. And processes use virtual addresses. Okay, because processes cannot use physical addresses because hundreds of things are running, hundreds of processes are running, and then OS dynamically gives space to each process when it runs, because otherwise, if you say that for all the processes area in physical memory is fixed, then of course you can run only limited number of processes, and that too you cannot change the machine. You cannot change dynamically run new programs then. Okay. So it means that at runtime physical memory has to be allocated. Okay, and that is done at runtime by OS using page tables. Okay, all right. So very often you will see that part of this address space. Of course, right now we for simplicity assume that address space available in physical memory in contiguous locations, but in fact the fact is that the whole address space is not available in main memory, right? Because it's we can, for this is the address space, right? We can split this into number of pages, and some pages may be available, okay, which are needed. All right, suppose code is very long, right? There may multiple pages of say 1K size. So only part of the code that's in execution can be brought to main memory. But for simplicity, don't get confused with the idea of pages at this moment. Assume that there is a contiguous chunk available corresponding to address space in physical memory for each process. All right. Okay. All right. So with this, let's start the third concept, the thread. Thread, we said, is single execution stream of instructions that represent a separately scheduled task. Okay, so basically, when we say single execution stream of instructions, right? So obviously your executable code has number of instructions, which are machine instructions, right? And then we execute these. As we execute, when we say we are executing a program or process, we are executing them. Okay, so instruction is same. Say this is instruction 1, instruction 2, instruction 3. Say this could be load word, This could be store word, this could be add, could be subtract, could be something JALR, something like that. Okay. Now, and when we execute something, then obviously we have what we change as part of execution, we write into memory, and then register value changes. The register can keeps the temporary values of any calculations, right, or manipulations. Okay, is that right? Okay, and also you may write something as part of execution, something in dynamic memory. Also, you use global variables. Okay, so now this is one thread, we can say, which is first time when we are executing a process. It's just single, when we have single execution stream of the instruction, we say it's a process and thread is same. Okay, now let's but note that there is some local data, and there is also writing somewhere in memory. Now, all or it's operating on some data, right? For example, when you're doing matrix multiplication, then the data given to you is matrix values of elements in matrix. So now if we say that key, all right, my first thread is using some data values, is operating on certain data values of matrix. At the same time, one can always start second execution of same instruction sequences and uses different set of data values. Okay, and then final result, both are executing. Okay, and final result may come out on certain memory locations. All right, so basically same sort of instructions are in execution. Okay, but where the program counter is, for example, in first thread, program counter could be here. It means that this instruction execution, so we call it say PC1, and for second thread, program counter could be here. Okay, and there are certain common things among them that we'll see once we go ahead, right? Okay, all right. The OS can run, suspend, and resume any thread at any point in time. All right, so scheduling of thread, of course we will study later that thread scheduling can be done in user space, but right now let's stick, we will have to think that threads are controlled by OS. Okay, OS can run, suspend, and resume any thread at any point in time. Okay, and all threads live in same address space because the instruction sets are the same, and then a lot of things are common, which we'll see in the next slide. Okay, and then we assume that that OS allows each thread to run. So it means that execution proceeds at some unspecified non-zero speed. Okay, so thread we can say is like a process, except that they share the same address space, thus they can access the same data. All right, so multi-threaded program has more than one point of execution. Okay, so we'll come to this diagram now.
Sir, could you
Yeah.
please explain the second point again?
Which one? This one? This one?
Finite process, progress axiom. Yes.
Yeah, all right, very good. So it's like this, that see, the threads are scheduled by OS, right? Now OS, say when there are multiple threads running, what do we mean by that? Suppose we have one CPU, one processor, okay, then only one thread can run at a time. Okay, all right, so let's assume first thread 1 is running. After some time, it process OS context switches and moves thread T1, saves its state somewhere, and then runs thread T2. And then maybe it will continue to run for some time. Then again, context switches to say T1 or maybe some other process or some other thread or some other process. Because threads are within process, multiple processes are running. So basically, but OS must ensure that each threads get time slice of processor. So it means that it must progress. So if thread T2 is for T1 is here, then after some time it should move further up. Okay, so there is it means that thread should not get stuck forever at certain point in execution. All right, so it means that all threads should progress. Okay, now of course there is a possibility that second thread that has started before first thread may get scheduled first, or I mean, there is no guarantee by scheduler that which thread will be scheduled first. Okay, it depends on scheduling policies. Okay, so we'll see that how it results that sometimes thread which is created at the end is finishes first. Okay, depending on whose schedule is what scheduler schedules. Okay, and then we need to have some primitive to synchronize them. But is it clear your answer? Did you get the answer?
Yes, sir.
It means that threads must progress. Okay, all right, that's all.
Yes, sir.
All right.
I also have a query. Sir, if a process is multi-threaded, so sir, will there be more than one program counter?
Of course, yes. We will exactly coming to next point, right? Okay, in this slide, you will see that. Okay, now don't think of hardware as a program counter. Program counter is nothing but a register. Okay, so you look only at the value. Physically, there may be one program counter. There is one program counter, right? Let's assume a single processor running multiple threads. So there is one program counter. And then this processor is switched between multiple threads. And each thread is running at different point in time. So the PC value, so when we context switches and moves the first thread out, we save its program counter value. And when we reinstate it, then we bring the same program counter back. Okay, so thread starts execution from there, right? So different threads have different values of the program counter. Don't get confused with hardware, register, and the value. Is it clear?
Yes, sir.
Okay, so this is what we see here is single threaded process or process. Okay, so we have in process code data, which is global variables, etc., and some files. Okay, it's basically some interface to files, right? And then it has registers, program counter value, and then stack pointer value or stack. Okay, so when we are running instructions, okay, like something that we have seen here. Okay, when we are running, sorry, okay, I will explain here itself. When we are running code and okay, and nothing but sequence of instructions, and you stop it in between, what all values it will have, and note that you have to restart from the same point. Then you will store the program counter value. You will have the stack values, which is various variables that you have, okay, local variables that you have. And then not necessarily all the register values are saved into local variables, because it may be operation may be stopped in between. Okay, so those registers are also a part of state. Okay, and we have to save these registers somewhere when we're context switching the process out. Okay, and apart from that, it has of course the same code remains the same. Global variables also is there, right? Okay, now when we move to multi-threaded process, okay, this is a process boundary or address space. So this is also address space, same address space. You know, if from one thread we fork multiple threads, then it looks like this. 3 threads we are using. So this is address space boundary, same addresses. So all threads use the same addresses. Okay. Now difference is that they share, if you look at this part, they share code. All are running the same code. All threads of a process are running the same code, changing the same data values, global data values. Okay, global variables, etc. And using same set of files. Yeah.
So is there a limit or number of threads we can use for a process?
Right now, at this point in time, assume infinite. Okay, so there is of course some restriction based on the resources that we have. Okay, but surely you can go up to say 1,000, 10,000 or whatever. So,
but sir, like I have a yes sir.
Okay, right now you assume that a large number of threads can be executed. Okay, of course, somewhere there will be limit depending on resource
Sir, I
availability,
have
right?
one more. Yes.
Yeah, please.
I have yes, sir, one more query. I have like as in the diagram it depicted that each and every thread uses one register, and in this we have only 32 registers. So how it will gonna manage 1,000 threads or something?
Okay, see, look at this way. Okay, just visualize. Okay, very important. So visualize it this way, right? When we say thread,
Sure.
it is nothing but sequence of instructions. Okay, and registers are the same, whatever number of registers we have studied, right? Same program counter in processor. Okay, note that we are not running threads simultaneously. We are not running threads simultaneously. If it is a single processor, we are not running them simultaneously. Okay, it's not the thread 1 is running, it's executing one instruction, thread 2 is running, is executing similar instruction or next instruction at the same time instant. It's not. Pipeline can contain, or your processor can contain only can execute only one instruction, a set of instructions, right, corresponding to a process, corresponding to a thread. So when we say a second thread is running at this point in time, assuming that we have single processor, okay, we are context switching one process out, okay, storing all these values here which are local to thread. See, all others are, see, something that's shown on top are common across threads, right? So the one which is shown here, you can see a line here. These are common across all threads. Okay, so to answer your question again, okay, so when we context, so basically we are running one thread at a time. We are moving the thread out, saving the state. We are, when we say we are saving state, we are actually saving the registers, PC, and it's like these values. Suppose this thread is running first, okay, and it's moved out context because scheduler will schedule out threads, right? It's not that thread or program is run to completion. It's not that. So it's moved out. Then second thread, this thread T2 will be brought into the CPU. When we say it's brought into CPU, all register values which are stored somewhere will be brought into the processor. So processor registers will get set with the values corresponding to what has been save, and then this stack will be used for further changing the values of variables, etc. So mainly when we context switch, essentially what we do is that we move the register values including PC and stack pointer back to processor. Okay, you get the point?
Yes, I get the point, sir. But I like
Sir,
one
I had a
like
yeah. Okay.
brother. Can you please?
Yeah, go ahead.
Sir, like if we are using only one thread at a time, then sir, why do we need multi-thread? Why can't we done like all our work with single thread?
Okay, we'll come to that point later. So it's like this. First reason is that, okay, when we have, right now we are assuming that we are doing a very plain simple job of execution calculation, a plus b's and all that, loading, storing, etc., etc. But I'm giving a very simple answer. There may multiple answer, will come to that later. There's a separate slide on it. But let's assume that there is one IO operation happening. You are as a part of instruction, you want to read something from file. Okay, and you know that IO is going to take how much time? Huge amount of time. Okay, and at this point time, almost like maybe let's assume 10,000 cycles. Okay, processor cannot wait for it. It will context switches. Now, second thread, which is doing the similar task, can run at this point in time. And when it does IO, then it will again be blocked. Now, question is that you may ask is that why both threads need to do IO? Yes, you can. For example, suppose you are a web server. Okay, then there are multiple users who are coming. So multiple data streams are coming. And for first user, for example, wants to fetch a page and then page is available on hard disk. At this time, same code that can serve second user or some other task for the same user or data collection part of the same user or some calculation for the. So that way we have, fast progress. I mean, same thing we can execute faster, right? Had we had one thread, then overall time is more. While first thread is blocked, second thread can do some task. That's the first answer. Second answer we'll see is that multiple threads can be run on multiple cores. That's advanced topic. Okay, then there is a question of, how do we do it? What are, how do we manage caches and all that? Those things come into picture. Now note that what is common, what is local to thread and what is not local, what is global or what is common across all threads. Note that code is the same, data is the same. Okay, when we say data, essentially which is shared across all is basically same as the one that is in process, which is across all threads, right? And then files that are opened are the same because file descriptors are the same.
Yes, sir, I got my point.
Okay, anybody, any other question? Because it's a very tricky thing, and not many people understand this concept easily, right? Even in industry, I have not seen many people able to explain this concept. Okay, all right, so let's go ahead. So thread encapsulates concurrency. So one thread is blocked, other thread will continue to execute. So we call this as a concurrent execution. We don't call it parallel execution. Okay, and thread is an active component. Of course, address space encapsulate protection because each program counter is restricted only to the to access only certain memory location corresponding to address space. Okay, all right. Now this is the address space. And part of this, of course, is OS. Right now, we are not assuming that part of this address space OS, etc. All right. All right.
Sir, I have a question.
Mm-hmm.
Sir, where does this when we save data for registers and PC program counter? So where do we save in this memory address?
Then if you repeat, your voice is breaking.
Hello.
Yeah.
Sir, we have to stop threads for squaddling other threads. So sir, we have to save registers and PC.
Yes, yes.
So sir, where do we store them in the memory address?
So good. Very good. We can't save it in this area, right? We can't save it. So there has to be some different data structure for that, which OS will manage.
So, sir, like we have Windows, Linux, and Mac OS, sir, both all three have different approach for that.
Yes, they may have different approach, but common data structure or similar concepts are used. For example, whenever OS, who will switch the process out? Process itself will not switch it out, or thread will not switch itself out. Thread may want to run infinitely as long as, right? In thread, so somebody has to switch it out so that one thread does not hog all the resources. So the responsibility is on OS. Okay, so OS must create some data structure to save the state of process or thread when they are in suspended state, right? And there is some data structure called, for processes we call it process control block. For thread we call it thread control block. Okay, and thread control block will save the value of PC, stack pointer, and registers, plus few other things it wants to. All right, and so this is a separate data structure managed by OS. So this will be corresponding to thread T1, say for example. Similarly, there will be one for T2. There, it's a kind of linked list. We will study that later. Same data structure could be the same, for T2 and so on. And whatever thread is to run, for example, the T1 is to run, the OS will take all the data and load it onto processor, register, program counter, stack pointer, etc. All right.
Yes, sir.
Okay, all right. Let's move ahead.
Sir, I have one doubt.
Yeah.
So as you said that we can run thread on different cores.
Yeah.
So is it possible to run that thread parallelly rather than concurrently?
Yes. That's the reason we run it on different
On
cores.
different cores.
Okay. It is responsibility of OS to run threads, multiple threads and multiple cores, but there are a lot of complexity in doing that. When you run, for example, you will create and run thread as part of exercise, then it's usually done in one processor, because then OS has to be ready to do all this task of running on multiple cores. Okay, all right.
Yes, sir.
So thread is single unique execution context. And something that's local to it is program counter, register, execution flags, stack, and memory state. Memory state is nothing, values of local variables, etc. Okay, all right. So memory state is this, and all the remaining ones, right? All this is called processor state. I am telling you this because processor state has to be saved somewhere else, while stack, memory, etc. will be in address space. Okay, all right. Okay, thread is executing on a processor or core when it is resident in process registers. Okay, so if the T1 is running, when we say T1 is running only when all the registers corresponding to that thread are in use. Okay, and or the values are corresponding, these register contains value corresponding to the thread. Okay, all right. So these points we have already covered. PC, this already covered. Okay, all right. So this point you already know. The stack pointer, of course, will point to the stack in where is a stack? Stack is is a part of address space that we have studied, right? So there is a user stack. The stack pointer points to this one. So stack pointer is a register in processor that we have studied. Okay, all right. So these points we know now. All right. Any question? Okay, all right. So then this point also we have studied that the point of context switching, the register state of the running thread is saved in thread control block. Right. So when thread is suspended, assume the thread is running and then it has to be moved out because something else has to come in. Okay. Then its state is not loaded into processor. So it's saved somewhere. That's in TCB. Okay. All right. So, and correspondingly, processor state points to some other thread which has been brought in, and program counter at the end point points to some thread that has been brought in. It's not pointing to the old thread. All right. And the copy of the last value of his register is stored in somewhere, right? Say TCB, for example. Okay, all right. So now when we are running multiple threads, how will it look like? So all threads share a process state, right? That we know. Okay, so this is and then of course they will all threads will have same address space. Okay, all right. Then what is common among them? Okay, code is common, initialized data is common, and then there's a different thread for two threads. How about heap? So heap is kind of common because assume that two threads are doing mallocs. Okay, so they are doing malloc. Basically the memory is being allocated to them. Okay, now when you do thread programming, then one has to take care that accidentally you don't use some other thread's data area, but of course you can. Okay, now when we say the threads are different, stack is different, it means that local values, register value, etc., right, whatever, or local variables, etc., not registers, local variables, etc., for both are different because both threads are in different state of execution. So if the thread 1 is here, thread 2 could be here, right? So register values, etc., and corresponding variables will be different. All right. Okay.
Sir, one more thing. Sir, if one of them changes the global variable, value of global variable, sir, doesn't it affect the execution of second thread also?
Yeah. So what is here that is to be taken care of. So what is a global variable here? This is where threads will share something with each other. So basically, certain things, finally you have both threads are doing some calculation and both may modify same global variable. Nothing wrong. So it's essentially you are not assuming, like when we declare a global variable, is visible to all functions, right?
Yes.
In a program. Similarly, global variables are visible to all threads. Okay, so when you do, that's the reason thread programming is complicated. If you don't want to use this kind of thing, then you have to take care of it by other mechanisms. Okay, all right.
Excuse me, sir.
Yeah.
Sir, here we can see that the stacks for thread 1 and thread 2 grow in the same direction, right?
Yeah.
So we have to decide at what point do we start the like stack for thread 2, like after leaving some space.
So that's the OS response. This is what OS design is. Okay. And usually this, okay, this is a whole, address space is quite huge. Okay. However, you are right. In fact, I would ask you to do one exercise that heap grows this way, thread grows this way. When can they overlap? So there is a one in security course if you do, but anyway, I will give you exercise to you. Nice that you reminded me. Okay. There is most common vulnerability that is there in Windows system, Windows OS, is called stack overflow. Okay, if you search for it, which is, this is possibly the magic for hackers, right? Hackers use this technology. Okay, such that we just overlap this. Okay, so in the process, you get access to a lot of things. So we'll study that later. Yes, there is a theoretically it's possible. Theoretically is possible, but then it's a responsibility of OS to manage it in such a way that they don't overlap each other, right? And second thing is, of course, there is no privacy between threads, because threads are in the same address space, so they can access whatever they want to. Okay. So here, let's assume that, okay, at this point in time, you assume that these are initialized data, because we use also what static data, right? And also use global. So both are there. So just let's assume that they are reading here something that is static or initialized data. Okay, all right. So we will discuss these things in more detail as we go ahead. Right now, my idea is to give you just the basic concept, what happens in thread. We are not going into great details into thread, which we'll do after few lectures. All right. Okay. So now let's come to the fourth concept, which is dual mode of operation. So now with this four concept, we will have some idea about how OS works. That's the idea, right? We are not getting into great details right now. Okay. Now note that processor, is basically, it does not have intelligence of its own. It's just hardware. Okay. And if the process is running, it can hog the resources forever. Okay, that's first thing. Second thing is that a process is running and it can, it can do certain critical operations which are not supposed to do, because if you can access even some important routines, for example, operation of cameras or operation of say some device, IO device, right? Then it can do a lot of malicious things. Okay, all right. So that's the reason the OS, the whole system is designed in such a way certain tasks can be done only by kernel. So user can say that do it for me, and then OS will do it for the user, right? But the user process is not allowed to read certain locations or do some tasks which they are not supposed to do. Okay. So the question is that, can a user access OS code and data? Obviously no. So we can think of system with the following diagram. Okay, there is a user mode and there is a kernel mode. Okay, so processor is either is running process either in user mode or in kernel mode. Okay, all right. Kernel has full hardware access. So kernel process can access anything in the system. Okay, all right. And wherein user have very restricted access. Okay, so if user wants to access something in the hardware, okay, then it has to make a request to kernel. Okay, and that is through interrupts. Okay, or through system calls. Say for example, reading and writing a file. When we say reading or writing a file or reading from a file, the file is in hard disk. Okay, and then using this system call, a user process can say get me data from this file, and then the rest of the task going to hard disk, managing hard disk, make use of device driver, etc., and then getting the data and presenting to user in certain way. All right, and so basically the program, when we are running a program, when we do IO or we do certain operation, it immediately gets into kernel mode. Okay, and then after, when kernel has completed a job, it may go back to this user mode of the same process, or other process can be scheduled.